Hi everyone, this is Mrs. G, and today we're going to talk about exponential growth and decay functions. But first, please pause the video and give this warm-up a try. All right, go ahead and check your work here. So for this first t-chart, I use this function, f of x, so you're raising 2 to these powers. And just a reminder that a negative exponent causes a reciprocal action. It does not make your answer negative. So we get something that looks like this. And then for g of x, we have 1/2 to the power of x. So we actually get the flipped values. So you get a graph that's actually reflected over the y-axis. So for both of these functions, they both have a domain of all real numbers. This graph, both of them are going to go to left and right forever. And you can see that both of the graphs are getting really, really close to y equals 0, which is the x-axis. But they'll never quite touch it. This is called an asymptote. We're going to talk about this on the next slide, but it does dictate our range. So our range is everything above 0, so 0 to infinity, but again, we'll never quite reach 0 because it's impossible to take a number like 2, raise it to a power, and end up with 0. All right, so today we are going to be talking about exponential functions. Exponential functions are functions in this form, y equals a times b to the power of x. Notice only b is being raised to the power of x. So just by definition, if it's an exponential function, the base, which is b, must be positive, and it cannot be 1. So that is a very important definition that you need to know. The base must be positive and cannot be 1 to be considered an exponential function. Now, one thing that we can do is certain exponential functions can be classified as either exponential growth functions or exponential decay functions. So for both of these, that a value out front must be positive. If a is negative, as you can see down here below, we would still call it an exponential function, but we wouldn't classify it as growth or decay. So if we're going to classify it more specifically, that a value must be positive. And then we have two scenarios. If your base is bigger than 1, we would call it an exponential growth function, because what you see will happen in this case is that your graph is going to grow as it approaches to the right. So as x approaches positive infinity, my y value goes up. It also approaches positive infinity. And if you, again, have that positive a value, but your base is between 0 and 1, we call this an exponential decay function. Just like you saw in the warm-up when it was 1/2 to the power of x, we have a decreasing graph. So as x gets larger, my y value gets closer and closer to 0. So we call this exponential decay. Now, both of these graphs, like we saw in the warm-up, have what's called an asymptote. An asymptote is a line, they can be horizontal or vertical, that your graph approaches really, really closely. So you can see that both of these graphs have horizontal asymptotes at y equals 0. So they're going to get super close to the x-axis, but they will never quite touch it. And then just a little bit more vocabulary. That b value, the base of your exponential function, we can call it the growth factor or the decay factor in these two cases. But again, this only works if we have an a value that is greater than 0. All right, let's look at one of these functions together. So first we're going to look at this graph and decide if it would be considered exponential growth or exponential decay. So if you look, we can see that our a value out front is positive, it's just positive 1, and we can see that our b value is 2/3. So since 2/3 is between 0 and 1, we would call this an exponential decay function. So you'll see that as we start to head on to the right, our graph is going to decrease and approach 0. All right, so let's complete our t-chart here. So remember, when we have a negative exponent, it causes the numerator and denominator to flip. So it actually becomes 27 over 8. If I cube both of these numbers, it's 8 over 27, but then because it's negative, we have to flip it. Same for negative 2. I square both of them, so 4 over 9, but then I have to flip it. So 9 over 4. This one, I just flip it, 3 over 2. Anything to the power of 0 is 1, and then we have 2/3. Then we have 4/9, and we have 8/27. Now to plot these, we just need to make sure we're between the correct two integers. If it helps, you can plug them into your calculator to get a decimal approximation just to see where the points fall. So this one is 2.25. We know this is 1.5. So we can do -3 and then a little more than 3. And we have -2 and a little more than 2. We have -1, 1.5, 0, 1, 1 2/3, 2 4/9, and 3 8/27. So if you connect your graph, it looks something like this. So you could see that as we move to the right, our values do get closer and closer to 0, which is what makes it an exponential decay function. So for these functions, regardless of what the base is, our domain should always be all real numbers. Our range is going to be 0 to infinity again. And you could see that our graph is getting really, really close to this, to the x-axis, which is the equation y equals 0. So anytime you're making a horizontal line equation, it's going to be y equals some constant. So when I ask for the asymptote, it should be an equation. And then for the end behavior, we can see that as x approaches positive infinity, my y value is actually approaching 0. I know usually when we did polynomial functions, our end behavior typically goes to positive or negative infinity, but end behavior could also approach a constant. So it is going to approach 0. And then as x approaches negative infinity, so on the left, you can see that my graph is just going to keep heading up. So f of x approaches positive infinity. So the right side approaches 0 and the left side approaches positive infinity. All right, so go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. This time our b value is 3, and since 3 is bigger than 1, this will represent an exponential growth function. So check your coordinates, check your domain, range, and asymptote equation, and then for the end behavior, this time it's the opposite of the last example. So as x approaches positive infinity, f of x approaches positive infinity, and as x approaches negative infinity, f of x approaches 0. All right, so now we're going to talk about a specific type of exponential function, which is called a natural base function. So natural base function is a exponential function that has a base of e. So whenever you see the variable e in math, it represents an irrational number, which is a decimal that will continue infinitely without repeating. And here you can see some of the digits of e. Okay, so it's simply a function whose base is this irrational number. And we will approximate e. Sometimes it's really common just to approximate it with 2.7. So if you have a base e function, again, we call it a natural base function, it acts just like any other exponential growth or decay function, except in how you define whether it's growth or decay. Because the base is always going to be e. So what will change this time is what you see in the exponent. So you'll see that we have a times e to the rx. So essentially, if you see a positive exponent, so if r is greater than 0, then it will be an exponential growth function. So it will increase as you move to the right. But if you see a negative up in the exponent, or if r is less than 0, then it represents exponential decay, and you will decrease or get closer to 0 as you move towards the right. So that's the only difference here. The base is always going to be e, but sometimes the exponent will be positive, making it growth, and sometimes it will be negative, making it decay. Again, when we graph these functions, we will just use our scientific calculator, which again has an E button to help us approximate these values so we can plot them. All right, so let's give this one a try. All right, let's give this one a try. So here we have e to the power of negative 0.5x. So here, since we have that negative r value, we know that this is going to represent exponential decay. And you'll see that when we start to plug in these points. So here we're going to do e to the power of, and if you look at your scientific calculator, e to the x is right above a button that says ln, which stands for natural log. So if you hit second ln, you can actually plug in negative 0.5 and then times 0.3, or sorry, times negative 3. And the decimal approximation for that, we'll just go to the nearest tenths, will be about 4.5. And then we can plug in negative 2, and we get about 2.7. And then we can plug in negative 1, and we get about 1.6. Anything to the power of 0 is 1. And then you can plug in positive 1, and we get 0.6. And then you can plug in 2, and we get about 0.4. And last, we can plug in 3. Gives us about 0.2. So if you plot those points, again, we're just kind of approximating where they are. You can see that we do have that decay function. It's getting closer to 0 as I move to the right. So anytime you have this base e function, or a natural base function, we are just going to use our calculator and get decimal approximation, so it's not too bad. And then if you look at the shape of the graph, it looks just like any of the other ones that we've graphed today. We have a horizontal asymptote at y equals 0. Our domain is all real numbers. Our range is 0 to infinity. And as x approaches positive infinity, we can see, again, that means moving to the right, my y value approaches 0. And as x approaches negative infinity, which means to the left, I'm going up. So f of x approaches positive infinity. So again, don't be afraid when you see a base e function. It just means that your base is about 2.7, and that you'll just have to do decimal approximations to plot your points. All right, go ahead and pause the video and give this one a try. You're just graphing e to the power of x. All right, go ahead and check your work here. Here's the decimal approximations for those coordinates, and then just check your end behavior. To the right, your graph goes up, and to the left, your graph goes down. All right, so now we're going to talk about a couple different types of exponential models, which is ways to model real-life scenarios with exponential functions. So exponential models are actually extremely useful. We will use them a lot. It's really good for modeling anything that increases or decreases by a fixed percent, which is many things in life, especially financial things, will often be modeled with exponential functions. So here's just a basic exponential growth or decay model. So this is for anything that is simply increasing or decreasing by a fixed percent. So if you are increasing, you're going to use this form. So it's a times 1 plus r to the power of t. So for this, a will represent the initial amount of whatever it is. It could be the population of something. It could be the number of bacteria. It could be, I don't know, a dollar amount. So it's your initial amount. And then you do 1, and then you do plus r, which is the percent increase in this case, as a decimal. You do need to make sure to rewrite it in decimal form. And then you raise this to the power of t, which is whatever unit of time you're working in. Could be years, could be days, it depends on the scenario. And then that 1 plus r, the entire thing together, is essentially your b value, so we would call it the growth factor. Now, if in the scenario, what the initial amount is decreasing by some fixed percent, we would use this exponential decay model. The only thing that's different is we do 1 minus the percent decrease as a decimal, and we would call this the decay factor instead of the growth factor. All right, so let's look at this example where we have a model that approximates the value of a car in thousands of dollars. And here's the model. Y equals 25 times 0.85 to the power of t, where t is the number of years since the car was purchased. So first they asked, does this model represent an exponential growth or decay function? So again, whatever is your base, whatever ends up being your base, we use to determine if it's growth or decay. So I see that 0.85 is less than 1. Well, it's between 0 and 1, which makes this an exponential decay function. So this is just like we did before. But here they're asking us, what is that growth or decay factor? So whatever this is would be that growth or decay factor. So 0.85 is the decay factor. Now for this next one, we have to do a little more critical thinking. They're asking, by what percentage does the car increase or decrease in value each year? So first, we know that it's going to be decreasing because it's a decay function. But just remember, for our model, it looks like this. So whatever the base of your exponential term is, becomes 1 minus r. So you could see that 0.85 is 1 minus r. So I could say 1 minus r equals 0.85. So my r value, which is going to be the percent increase or decrease, is actually it's not 0.85. It's 1 minus 0.85. So our r value is 0.15. Which means that we are decreasing but we're not decreasing by 0.15%. Remember, this is the percentage as a decimal. So if you take your decimal point and you move it over 2 spaces, that gives you the percentage. So it's decreasing by 15% each year. So just be really careful. It'd be very easy just to look at this and say, oh, it's decreasing by 85%. But remember, the base represents either 1 plus r or 1 minus r. So you have to actually find r, not your entire base. And then it's asking, what is the initial value of the car? So initial value would be when t equals 0. So let's substitute t equals 0. Y equals 25 times 0.85 to the power of 0. Well, anything to the power of 0 is 1. And remember, only 0.85 is being raised to this exponent. So it just ends up being 25. Now, we know that the car is probably not just worth $25. That doesn't make a lot of sense. So if you look back at the original problem, it says that y represents the value of the car in thousands of dollars. So that means the initial value of the car is $25,000. So that's the initial value. But then they also ask us to find the value after 5 years. So for that, we'll say t equals 5. So we do y equals 25 times 0.85 to the power of 5. And this we're going to plug into our calculator. And I'm going to round it to 3 decimal points. So when I convert it to thousands, I have 3 decimal points to move it over. So I have 11.093, which would mean 11,000 $93. And then they also would like the value after 10 years. So that's when t equals 10. So I simply replace t with 10, plug it into my calculator, and I get y equals 4.922. So $4,922. So there you go. So you can see that this is a real life scenario where using an exponential model would be really useful. So we can use it to help us predict the value of something that is increasing or decreasing in that way after a certain amount of time, which again is very, very useful in real life. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. This is another decay function, and just be careful. The percentage it's decreasing by is not 92%, is not decreasing by 92%. It's actually maintaining 92% of its value each year. And if you use that 1 minus r equals whatever your b value is, we see that r value is 0.08. So it's actually decreasing by 8% each year. And then here are the different values after 5 years and 10 years, and then this is the initial amount. All right, let's look at another one together. This says in 2015, the world population was about 7.38 billion people. During the next 5 years, the population increased by about 1.09% each year. We're going to write an exponential model that represents the population in billions, t years after 2015, and then we'll use it to estimate the population in the year 2020. So since the population is increasing, we're going to use our growth model like this. So remember, A represents the initial amount, so it's going to be 7.38. We're modeling it in billions, so I'll leave it as 7.38. And then our R value is going to represent our percentage increase as a decimal. So I do need to move it 2 decimal spaces to the left. So our R value is going to be 0.0109. And then T is our independent variable, so we leave it as T. So we have y equals 7.38 times 1 plus 0.0109 to the power of t. And I guess we can actually add those two numbers together for our final model, 1.0109. So this is our model. Then they asked us to use the model to estimate the population in the year 2020. Well, if t represents years after 2015, that means that we're going to be plugging in t equals 5. So it's 5 years after 2015. So you do y equals 7.38 times 1.0109 to the power of 5. And then we'll get a decimal approximation for this. So plug it into our calculator. And we get about, and we'll just round it to the nearest tenths, and I'll just write billions after it for my final answer, 7.79. So the population was about 7.79 billion people. So again, here's just another good example of how useful these types of models can be. They are very commonly used to model different population growths or decreases. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. We're using the growth model. Our A value is 1.04 and our R value is 0.0205. So here's our model, and then you can plug in t equals 8 to estimate the population in the year 2018. All right, so the last thing we're going to talk about is this idea of compound interest, which is another really common use of our exponential function. So compound interest is when you're earning interest on your money. So you have money in a bank account, for example, and your bank says, I'm going to pay you 3% at the end of each year. So they look at how much you have in your account and they take 3% of it and then they pay you that money. Now, if you have compound interest, that money gets added to your initial amount, and then the next time you earn interest on that new higher amount. So this means that you earn interest on your interest, which is good for you. It means you will be making more money over time. So there is a formula that we can use to help us calculate the amount of money we will have in our account after T years. So first you start with your initial amount. In finance, we often call the initial amount the principal. So principal just means your initial amount. So that's going to go here. And then we have 1 plus R, which is your interest rate as a decimal, your annual interest rate as a decimal, divided by N. So N is the number of times per year your interest is compounded, which essentially means how many times a year does the bank look in your account and pay you interest. So N goes here, but you also see N up here. So then you raise that to the power of N, which again is the number of times per year your interest is compounded, times T, which is the number of years that have gone by. T is going to be our independent variable, so you can plug in any time, and then what you will find is the amount in your account after that period of time. So again, this is a super useful formula for us to know because compound interest is a very common thing. A lot of people have accounts that earn compound interest. All right, let's give this one a try together. So this says you deposit $9,000 into an account. Well, that's going to be our principal amount. So P is $9,000. And you deposit that $9,000 into an account that pays 1.46 annual interest. So that means that R is going to be 0.0146. Remember, we need the interest rate as a decimal. Then we're going to find the balance after 3 years when the interest is compounded quarterly. Quarterly means 4 times a year, so N is 4. So now we're going to use our compound interest model. So P times 1 plus R over N to the power of NT. I know this model looks a little intimidating, but it's super easy to use as long as you know the initial formula. So A is 9,000 times 1 plus 0.0146 divided by 4 to the power of 4t. And this is our model. And again, we are going to be using our calculator to get these values, so this is no big deal. You can actually type this into your calculator exactly as you see it, okay? So if we want the balance after 3 years, we're going to substitute t with 3. So we get A equals 9,000 times 1 plus 0.0146 divided by 4 to the power of, one thing, we could just say to the power of 12. We know 4 times 3 is 12. If you're going to plug it into your calculator and you don't want to do the multiplication yourself, so you could type it in like this, please just make sure you're grouping that 4 times 3. So you do to the power of parentheses 4 times whatever your t value is, just to make sure that all of it ends up in your exponent. Okay, so give me a second. I'm going to plug this into my calculator. And we should get about 9,402, and I'm going to round to the nearest hundreds. It's money, and money is rounded to hundreds, so let's do that consistently. So we have $9,402.21. So you can see that just by doing nothing, literally just by leaving your money alone in this account, in 3 years, you've made over $400. And again, we are earning more because it is compound interest rather than just simple interest. All right, go ahead and pause the video and give this one a try. All right, go ahead and check your work here. So our principal is 8,600. Our R value is going to be 0.0132. And because it's compounded monthly, monthly means 12 times per year. So our N value is 12. Here's my model, plug in T equals 4, and here's the amount of money you have in your account after 4 years. So maybe you figured out that with compound interest, the more often your account is compounded, the better off you are. You will make more money. So having interest compounded monthly is better than quarterly, and quarterly is better than yearly. So now let's imagine that instead of being compounded once a year or once a month, what if you were compounded continuously? So every fraction of a second of every single day, you were earning interest, that interest is added to your account, and now you're earning interest on that interest. So that's called continuously compounded interest. Now, when you have continuously compounded interest, we actually have a different formula for it. So this formula is still a compound interest formula, but it's for continuously compounded. And we only use it in that very specific scenario. So for this scenario, it's A, which will be the amount of it in your account after T years, equals P, which is still the principal, times E to the power of RT. And R is still the interest rate as a decimal. So you could see that now we have a base E function. So remember, E is that irrational number we learned about that helps us model continuous growth. So this, again, is the formula we use for this very specific case. All right, let's look at this same scenario. We have that same scenario from example 6, but now instead of being compounded quarterly, we're going to be compounded continuously. So let's see if we end up making more money. So our principal is still 9,000. Our R value is 0.0146. But again, now we don't have that N value because it's compounded continuously. As soon as you see those words, you know that we are using this model. So A equals P times E to the power of RT. So A is going to be 9,000 times E to the power of 0.0146 T. So this is going to be our model. And so if we want the balance after 3 years, again, I'm going to plug in T equals 3. So we have 9,000 times E to the power of, make sure you're grouping your exponent, 0.0146 times 3. So we'll plug this into our calculator. Give me 1 second. And here we get $9,402.96. Now, if you compare this to your answer from example 5, we do actually make a little bit more money here. I believe the last one was 21 cents, and here is 96 cents. So maybe you're thinking, well, does it really matter? That's such a small amount of money. But you have to remember, this was only after sitting in an account for 3 years. It's a pretty low yield interest rate, 1.46%, is a little low. And $9,000 is not a super, super high principal, but imagine you had a large amount of money that was earning a little more interest and you left it there for 20 years. Something like being compounded continuously could have a much bigger effect. So again, you will always make more money if you're compounding continuously, but especially if it's a short amount of time, that amount might seem negligible, but it will always be more. The more often you're compounded, the better off you will be. All right, go ahead and try this last one on your own. All right, go ahead and check your work here. So here's the model. You're going to plug in t equals 4 to find out how much is in your account after 4 years. And if you compare this answer to the last you tried, you do end up with a little bit more money than when you were compounded monthly. So again, compounded continuously is going to be more beneficial than being compounded monthly or quarterly or yearly. All right, that's all for today's video. Thank you so much for watching.